Hello, guys. So several questions. So I actually just this very moment received a message from one of you asking me if there are going to be any penalties on Friday. My God, this question almost makes me feel like I'm disappointing you. Right? There are no penalties. Just what am I going to do? How is the exam coming along? How many of you are close to submitting the exam? Test is hard. And that's the second question. I am now making the final. So Nicholas, you're saying test is hard, yes? Or you agree? Well, I'm glad I did not disappoint you. So here is my question. I'm making an exam on the for the final. I do not know how much do you appreciate my creativity and composition, right? I mean, I just feel like I'm sitting there, and I have this creative thing. I can ask so much harder. I can make it so much more interesting, right? You don't enjoy it. I should keep it simple, boring, and gray. Mediocrity, yes. Exactly, Gustavo. Right? No, right? I have so many questions. They're so confusing that I am confused by them. Right? So, and I feel that that's not confusing enough. Well, it's more than fine. In other words, it's not fine, Chiara. More than fine.
晚上也给我来个串一天，让你就不能吃，好几天都不能吃。你问你要不要今天晚上来个串？
I see how people are paying attention to my class. Yes, Lauren? Well, at least you have good conversations with friends and fellows. That's nice to know. So, all right, just give me a sense, guys. So the test, very hard. Did you enjoy it? Was it excruciating and still enjoyable because you're masochists? What is the actual situation? I don't know how you enjoy it or not. I am afraid. I feel like I haven't given you enough. That's how I feel really about all those things. It bothers me. I cannot sleep at night. I just think they're going to leave this class, and will they know probability? Will they be able to think, or will they be? Okay. So concerned for your grade. I know that I'm not very. Maybe you don't believe me. I mean, I hope you don't believe me. That makes you work hard, but I am rather. I would not call it fair because I just give grades like handouts. Some person wrote me from last semester, sadly, about my bubbly and wonderful personality and how they appreciate me for some strange reason now. And I wonder, what recommendation is this person preparing me for exactly, right? What do they want from me? But some people say bubbly personality. Some people, a year later, I forgot almost about this person. So, I mean, the reason I mentioned that is, I am not a very harsh grader. So you have a safety net, right? You might imagine you're failing the class, but probably I will pass you. That's kind of the Russian way, just to tell pass, right? But if I get irritated, if I have this feeling that you cheated or lied to me, I get offended a little bit, right? Just get annoyed. I get annoyed that I give a good grade to a bad student and a bad grade to a good student, and then I might punish you, right? But if you try honestly to solve the problem, and even if you're not successful, for this level of class, I'm hoping it's a sort of indication of where you want to go or how hard it can be. It's not even nearly as hard as it can be. And I hope that it will encourage you to just study it on your own, right? Just keep your interest, that's all it is. So there is a sort of safety net, like a basic income, as people like it, right? So say, and my basic income is so high that the grade is almost meaningless. You understand? It's almost like you're paid with paper, right? You understand? I passed people very frequently, to be honest, that if I were assessing them the way I assess myself, I would have failed them below F. But I passed them, and not just pass. Good? I don't want to tell you what's that basic thing, but there is a basic grade income, right? Socialist type of thing that I do for you that makes grade completely valueless, but of course education has long ago become valueless, formal education. Very rational, yes. So relax about passing it. Just I ask questions more so to just hopefully get something in there. That's all, right? That's the reason I asked whatever questions I do. So let me know based on that. I'm gonna, my assumption, because I also don't want to grade too much, I'm gonna make the final slightly easier, right? But I want to introduce one question that is kind of yes. So my final is almost ready. I mean, actually, I could just mostly recycle something from before, since you don't want me to be too creative, right? So then that's what I'll do. Is that what you want? 10 questions. You don't know what you're missing. All right. So now let's talk about you. Most of you haven't replied, by the way. I don't know. So again, yes or no, very quickly. Yes, easy. No, hard. Well, what's the trap? Exactly, right? Okay, well, then I won't work too hard on the, maybe I'll just change one question and I'll leave this. I just look at this final and it's just so many questions are so boring. I don't like them, right? But, and I think I can replace them by so many interesting ones. But okay, if that's what you are up to, I'll let it be. On Wednesday, you might see the exam. Good? I'm not sure if it's easy, but it's not what I intended it to be, at least based on what you're saying. I might just change one question, right? I do not know what you mean easy, right? But I hope you would agree that it's easier than this one. For winter break, there is no break in the winter, you know. I mean, you continue studying probability, one question a day when it's over. Yeah. All right, guys. So let's talk about what I asked you. Hopefully you would find it interesting. So another student from a few semesters back messaged me and asked this thing that he says, well, it's given as a paradox. So this is what I messaged you, and I hope you had a chance to think about it. If not, let me just retell the story. So imagine you have coin and you know nothing about it. Yes? So this coin is tossed 14 times, and 10 are heads. You understand? 10 are heads. So you are forced to choose between two bets. Okay, so bet one is next two are head and head, and bet two, anything else. For next two. In other words, you can get head, tail, tail, heads, or tail, tail. Understand, right? So any of those outcomes, and you win if you decided for bet two, and you lose if it's heads, heads. Do you understand? That is the question. What do you pick? You're forced to pick between one or the other, and of course, you understand your gain or loss is the same for both bets. In other words, imagine that you will gain $1,000 and lose $1,000 if you choose bet one, and you win or lose, right? It basically depends on the outcome. If you get heads on bet one, you gain $1,000, and if not, you lose $1,000. If you pick second strategy, it's the other way around, right? If you get heads, you lose $1,000, and if you get anything else, you win. What do you prefer? I want to see a lot of answers since you are there. Probably the second one. And Nicholas is asking, is it a fair coin? Well, you saw the outcomes. We don't know anything about it. If it's a fair coin, it's easy to pick, correct? If the coin is fair, guys, obviously you pick which bet. Stop for a second. Coin is fair. Which bet? Obviously you pick if the coin is fair. 2, absolutely correct, because your chances of winning in bet 2, if it's fair coin, is 2 quarters, whereas and to lose is just 1 quarter, right? So it's 3 times more likely that you win if you pick bet 2 if the coin is fair, but you don't know what coin it is. And if you understand, guys, what is a fair or non-fair coin, simulate instead of using a coin, take a wheel. Take a wheel of fortune and divide it into 2 unequal sectors, right? If you divide it into 2 equal sectors, it's like a fair coin. If you divide it into unequal sectors, you can make any unfair coin. You understand? So it's more like a wheel of fortune divided into 2 sectors. And what happens is, let's say there is a red sector. Red sector is heads, and there is a blue sector which is tails. And out of 14 trials, the wheel of fortune stopped at a red sector. That's all you know, but you don't know what's the proportion of red to the total. So which now do you pick? That's supposed to be a trick question. Okay, that's supposed to be a trick question, and that's why the person asked me, and I thought it's interesting, and I thought I mentioned it in this class, so that you perhaps will, you obviously you know that there will be beta distribution on my final, correct? I mean, who can give a final without a beta distribution? It's just not possible. So here is the calculations. Here is how you can do them. Okay, can you see my screen, guys? I mean, no need to enlarge it. Let's see if I can make it. So yes, I mean, I can make it larger, but hopefully I can just trade it for you and you can see what I did. Okay, so based on what this person, I mean, I can tell you what calculation I did, and I can tell you what calculation was proposed. So if you are a frequentist, right? That's what the article or the blog that this person said. It said that if you're a frequentist, okay, I'll try to make it larger.
Look down at the bottom of the Mathematica window. There's a thing that says 100%. You can use that to scale the view.
Say it again, Barry. Down where?
Bottom right corner of the Mathematica window.
Bottom right corner of
where it says 100%. Yeah. Look at
100%.
Where it says 100%.
I see.
Click on that.
I see.
There you
Thank
go.
you so much. Very good. Thank you for your troubleshooting.
I love Mathematica.
I hate it. And I had to program stuff with it. I can show you if you want to see what I had to program recently. My God, I just want to break my head. But I'm impressed that
it is totally evil, but it's better than a lot of other things.
Yes, I mean, it's true. It's like having 1 pin in your butt. It's better than having 7. In that sense, I agree. Right? But best is not to have any. Yes. So now you see the display, correct? So here is what I did. So the frequentist approach is this. So they estimate the probability of success to be 10 divided by 14. We had 14 trials, yes, after all. and 10 were successes. So the probability based on this frequentist estimation of the probability is 10 divided by 14 squared for each of the trials, their independent tosses, correct? And that gives you 0.51 something, right? Essentially, it gives you 51% success, which means that if you believe that the probability is 10 over 14, you want to select procedure number 1, the bet number 1. Because that gives you slightly over 50% chance of success, and therefore the other one gives you slightly less than 50% chance success, correct? Whereas I did not calculate it like this. I mean, they in this article, they say, they just immediately made my calculation and I read the article, what they say there, right? And my calculation was, of course, this, which you recognize as what? You recognize as the beta distribution, correct? You understand it's a conditional beta distribution. So what is the 11? I don't have the beta factor because they cancel out. You understand? I mean, I just divided by this other integral. I just created a conditional. And if you understand integrals well enough, it's easy for you to create this conditional probability. And so what do I say? I say, okay, this distribution based on this information is what? We have 10 successes and 4 failures. We add 1 and 1 because we have to add, I think, 1 extra to the parameters, right? It's so basically because the number of successes is supposed to be, if you remember, it's supposed to be the power is a minus 1. So a minus 1 is the number of successes, right? So well, sorry, a is the number. That's always very annoying for me, by the way, right? The plus minus 1 really just always just messes my wires, right? So I am, if you make the mistake of plus minus 1, I would possibly forgive you, right? Because I just like left and right, turn left and right, it confuses the hell out of me. Left is always where I want to go to me, right? So if somebody tells me turn right or turn left, usually I just turn wherever I think I actually have to go, but I don't really regard their instructions. You understand? I have to really think about it all the time. I have to really kind of rotate myself and think, okay, what are they saying? Same thing with the plus minus 1. It really bothers me. But we can actually afterwards reconfigure. You understand how to update the distribution. So we initially began with parameter 1 and 1. Right? Initially, I think we begin with parameter 1, 1. It's uniform distribution. Once you update it, and you update it based on 10 successes and 4 failures, I think you add what? You add here, you add to 1, you add 10, and here to 1, you add 4. That's what I think it's correct. Okay. I hope I'm not mistaken, but we can just again correct ourselves. Correct? It's very similar regardless. Nicholas is smiling. Yeah. So. What about the numerator? The numerator is, I say, okay, if the probability is p, then the probability of success is p squared, correct? So that's so basically it's conditional. Given this p, given that the probability is p, the success is p squared. What's the probability that it's p? It's approximately this thing up to here is approximately the probability it's p. Do you understand? And they add up over, that's the integral is adding up over all possible p's. I hope you understand this this explanation. What is funny in the background? Do you see something? Ah, okay. I see. Oh, it's too bad. I guess this thing does not make you smile. I'm now I feel hurt and misunderstood. Okay. So once again, guys, I hope you can follow it. If you are not, we can maybe reevaluate how we carried out this calculation here. Okay. So how did I think of this expression? So we have, if we use the beta distribution updates based on evidence, right? So based on the beta distribution, we don't regard any experiment as telling us the probability. It only tells us the likelihood the probability is in a particular region. Understand? So initially we begin with this probability. We don't, before any information is given, we have beta 1, 1. Yes? Next, information is given. You understand? We had 10 successes out of 14 trials. Right? Having 10 successes out of 14 trials does not preclude the coin from being fair. It's possible if the coin is fair for this to happen, correct? And it's possible if the coin is almost very unfair to be the case. It's more likely if the coin is biased to many heads as opposed to the coin being biased to very few heads, correct? So after this information, we have this update. We have 10 successes for failures, right? What happens to the distribution? It is now a different distribution, correct? It's now beta 1 plus 10, right? And 1 plus 4. So it's now basically beta of 11 and 5, right? Beta 11 or 5, maybe in my calculation, I forget, maybe I need to subtract 1, but basically this is what you need to know. Be careful, right? I just did it this very moment. It used to be beta 1, 1, probably I have to subtract, 1, right? So we can check what happens, by the way, if we do that. Second. So I think, what is it? So I said here, that's plus 10, right? Plus 10. And because when we integrate, I think we subtract 1 here. So maybe that would be 9, and that would be 4. That would be 12, maybe, and it would be 4. Maybe, let's see, what is that making big difference? Yes, well, maybe it's like this, right? Just be careful, right? Just be careful about the point is that it's small, right? Be careful about the powers, okay? Are you with me so far? It's just in the integral. I mean, I'm not using the beta distribution, right? Just what I'm doing is I am using this information, this update information, which you should understand when you carry the calculations, correct? And because of this annoying thing that bothers me is that you have the p to the power of a minus 1, that type of thing. Be careful. I mean, maybe you don't need it in my calculation. I need to rethink how did I carry the calculation to begin with. Okay, so this is just a constant. This is, I think it's like I said before, not the change. So this is the constant. So the constant is beta 11 and 5. And now the distribution is probably something like this. It's probably leaning to higher values. Good? It's leaning to be a higher value. It's not absolutely biased, but it's probably more biased than just be, right? So it's like this. Make sense? And then what do you do next? Next, you want the probability that x is equal to 2. That means 2 successes. In the next 2 process, right? So what is that? So if we want to know in 16 how many heads, so yes. Just be careful. This is the beta. I should say this. The beta is just how the distribution is updated based on the evidence. Okay, so let me just be sure, Chiara, that what you said is right. So if we want to know in 16 how many heads, supposing that next, well, be careful in the phrasing. Beta distribution is the estimation of probability based on evidence. Okay, so the evidence in our situation was what? We had 10 successes, 4 failures. That's the evidence. Yes. So we now assume that we're dealing with a distribution which is beta of 10 plus 1 and 4 plus 1. So it's beta is of 11 and 5. Yes. So then what do? So the probability that x is equal to 2 is simply the probability that x is equal to 2, given that the b is equal to p times probability b equal to p, and you sum up over all p. You agree? That's just conditioning. Okay. Now, what do you get if you do that? What you get is 1 over, it's always 1 over beta 11 and 5, 1 over beta 11, 5. Yes. And then the summation is just an integral. So it's integral from 0 to 1, correct? Of what? Of x is equal to 2, given that beta is equal to p. This is just p squared, correct? So this part is p squared. Now, probability that beta is equal to p, it's the same as beta belonging to p all the way to p plus dp. Kind of like this, right? Because it's a continuous variable. This is the estimation. So what do we have? We have, this is where this is coming from. So p, so this is what? This is p to the power of 10. I think we subtract 1, given that beta is at p10, 1 minus p to the power of 4, right? Because that's beta equal to p, it's this number and together with this number, right? Because I think you just take the first number here, subtract 1, second number, subtract 1. So it's like this, yes? And dp. So this, together with what I underlined, is that probability. So what do you get? You get simply 1 over beta 11, 5. Integral 0, 1, this becomes p12, 1 minus p to the power of 4 dp. Yes. Now, what do you divide by? You see how I got this formula, and what is this number? This number is just the same thing, but here p is to the power of 10 and 4, right? So let's see. So here it should be p to the power of not 9 but 10 and 4, and we get, let me just check. So it's here it should be it's correct, 12 and 4 and 10 and 4. So it's something like this, I think. Yes. Yes. So that is just a constant I introduced. That's beta of 11 and 5, I think. Okay. And that is the number that we obtained before. Here it is. It's the 12 and 4. Yes. Correct. 12 and 4. Now I think it's this is now probably the right answer, right? You see the numerator is the conditional probability, and this is just the corrective factor. Because you have to understand what is beta. Beta is just this coefficient beta 11 and beta 11 and 5 is just a coefficient that's supposed to normalize the distribution so that you get probability 1 if you integrate over the entire distribution. Make sense? So do you see how the delta distribution is working? Thank you, Barry. Maybe I'm wrong. I mean, how do you know it's a correct result, right? I mean, don't trust anyone, especially experts, so-called experts. Never trust experts. So here is what we have. Okay, guys, and before I move on from this question, I hope you understand why it's interesting. Yes, isn't it interesting? It's claimed that we have here is one result and here is another result, right? So based on your viewpoint, it appears that that you are driven to completely contradictory conclusion. One says, look at this, choose to bet in favor of having two successive heads. And the second strategy tells you choose against having two heads. So who is correct? So according to the second calculation, the probability of head-head is about 48%, which means you want to choose against it. You want to say that based on the second explanation. But the first explanation tells you, no, you should choose for it. So I really wanted to assign it for your exam, but I decided, oh, okay, fair enough, right? I'll just tell you what it is. So, and besides, because maybe Chiara, I had in mind a much more sinister question. That's maybe why I decided to assign to talk about it at least here. But don't worry about it. Sinister questions should be welcome, because I will tell you what I think about them, and you either agree or not. And the state of confusion means it's the state of thinking, right? The state of people that are just pushing something and mentioning something with certainty very often, is a lack of thought. Maybe they are correct, maybe not, but they're just kind of like running against the wall. So which one of them, guys, do you think correct? At least I'll tell you what is my opinion. Nicholas says a second, and what about the rest of you? Is it because I mentioned that I did the second calculation right away when I saw the problem? No, here is, yes, guys? But too easy, maybe the too easy is the right answer. It just some things that are very difficult tend to break, right? Things that are very compound and complicated have many places where they break. So just because something is simpler, it doesn't mean it's less correct. Be careful. All right, so I guess I'm pulling teeth. You don't want to share your opinions. I can tell you what I thought of it. So it really, so I think of myself as a frequentist. In other words, I understand probability or the theorems based on frequencies, at least based on theoretical frequencies, not finite ones, you see? So if you toss a coin, you've seen experiments, how long does it take for convergence? How long should you toss a coin before you're very convinced that you know the theoretical probability? You should toss it maybe millions of times, right? I did simulations, you remember I showed you actual simulations, right? And based on those simulations and based on some questions that I ask you, you can see that convergence can happen rather slowly to the probability, correct? Which, by the way, also makes it, to me at least, very, it bothers me, when convergence is very slow, does probability even matter? I mean, does it help me predict anything? If convergence is very slow and basically my results are complete noise, maybe it doesn't matter what you really bet. That's also a problem, yes? But at least that's why when I tell you, I truly don't understand probability, right? I mean, I say this is what you do if you make a habit out of something, right? So if you buy a lottery ticket, you buy it once, I don't know what will happen. But if you buy it all the time, I can tell you that you will be just losing money, right? But that's about convergence, right? The same thing with this game. I mean, convergence is happening maybe slowly. But regardless, if you just want to know the probability, just to evaluate the probability, we can see that this information is definitely not sufficient to be sure that the probability is 10 over 14. Correct? It's very likely not to be 10 over 14 because there are many other possibilities, many other hypotheses that would lead to this result. In the coin, you can just calculate how likely is this result if the coin is fair? How likely is this result if the coin is slightly biased, you see, or even very biased? And you can just in the opposite direction, you can just have many estimates. So this result, I understand, still using frequencies. Just I have to take a limit to infinity, right? So what is this saying? It's just not assuming that I know the probability. So it says, given the probability is this is the result. Given the probability is something else, this is the result. So it gives you a measure of how the probabilities are focused around something, but not really telling you what the probability is. So I would have interpreted it this way. I think this is correct. And if you do it frequently, if you have, of course, many more trials, then both things will agree. It's just too few trials, so it did not converge perhaps to the good probability. And that's why the difference is visible. Interesting question, yes? What do you think, Nicholas? All right, and now let me confuse you further with my other problems. So we are on the last exponential problem. I do not know if you'll enjoy it, but it is based on a true story, just like movies are. You don't know how much of it is true, but some part is. So I mentioned I have, or more so had, a friend by the name of Dave. And we would take very long walks. I mean, I enjoy taking enormously long walks. So they might start at 12 p.m. and end up at 5 a.m., right? Walking huge distances. And we sometimes met by my house, sometimes by his house. And he would always be late at coming out, very late, so that I implemented what I called a Dave correction time. So this is my procedure. So suppose that Dave exits his house or arrives at the meeting with a distribution D that is exponentially distributed with mean 1/10. That's the parameter. Okay. That means that on average, you will see it in a moment, on average, 1/10 means that it will take him on average 10 minutes to get to a particular location. Good. So when he would schedule to meet by his house at 12, what I would do, I would arrive uniformly between 12 and 12:10. Because of the 10 average, you see? So I don't have to wait for him. Between 12 and 12:10, I just randomly arrive. Okay? And when he would be waiting by my house, let's say he comes at time t, I would still exit the house, maybe as a punishment, I don't know, right? Uniformly between 0 and 10, you understand? So between the moment he arrives, I see him outside of the window, I'll take maybe uniformly between 0 and 10 minutes to exit. Make sense? So here is the first question. Given that Dave has been waiting for me for the past 6 minutes by my house, what is the probability that he will have to wait another 3 minutes? You understand? So suppose it happens that he's already waiting for 6 minutes. What's the probability he has to wait an additional 3 minutes? Can you calculate? You understand, I am uniformly distributed from 0, the moment of arrival, to 10 minutes. I don't make him wait ever more than 10 minutes, but uniformly between 0 and 10 minutes. What do you mean, Gustavo? Using my brain alone? You can also use a pen. All right, let's calculate together. So this is the calculation. Simply, what's the probability that A is bigger than 3 plus 6? Given that A is already bigger than 6. And that's the same as the probability that A is bigger than 9, divided by the probability that A is bigger than 6. Correct? You'll see how I did it. It's just the intersection of those events. A is bigger than 3 plus 6 and A is bigger than 6. It's the same as just A bigger than 3 over 6, 3 plus 6, divided by the probability that A is bigger than 6. Yeah, cool. You see what I mean, right? I know it's also my question. So my questions could be dangerous. I don't know, right? I mean, maybe I didn't phrase it fully well for you. It's, you know. So what do you get? You get 1 over 10 divided by 4 over 10. It's just always the amount of interval you have here divided by total, divided by amount of interval you have here by total. So this interval is of length 4, total interval is of length 10, so it's 4 over 10. Make sense? That's what uniform, you can use that short trick. You don't have to integrate. It's very easy to see that the probability of a particular subinterval is just the length of the subinterval over the total interval. Yes, so it's 1 over 10 over 4 over 10. So the answer is 1/4. So it's a 25% chance that he has to wait an additional 3 minutes since he was already waiting. Yes. Now, question B, given that I was waiting for the past 10 minutes for Dave to come out of his house, what is the probability I will have to wait 10 or more additional minutes? You understand? So this is, you can guess, right? So I was already waiting for him 10 minutes. And what's the probability I have to wait another 10 minutes or longer? Oh, Camille, you are too nice. He is not exiting the house the way I do. My distribution is uniform. His distribution is exponential. Yes, which means what? Which means he doesn't remember. It doesn't matter. It doesn't have any regard. If I waited a century for him it's as if I just arrived. That's the type of person Dave is. All right, let me help you with the calculation. So the exponential random variable D is memoryless, which means the probability is just as if the waiting has just as if I just arrived and I have to wait 10 minutes. You understand? So memoryless means that it doesn't matter. The past is the past and forever buried. And it's as if just this very moment you start from scratch. So that means that it's just a probability that D is bigger than 10, which is the integral from 10 to infinity of 1 over 10 e to the minus t over 10 dt. Yes. And this equals to e to the minus 1. Right? Which is approximately 37%. You all understand how to calculate it. It's easy, right? Yes. So next question is question C. So annoyed, I complained to Dave that he is very inconsiderate. And he rebuffs this accusation with his typically cynical smug, saying that on average, we wait for each other the same amount of time. And he justifies it as follows. When I visit you, it takes you on average 5 minutes to come out. Whereas when I tell you to meet me by my house at 12, you typically arrive 5 minutes late, and I exit my house on average at 12:10. And that means that you actually wait for me on average 5 minutes. He waits for me on average 5 minutes. I wait for him on average 5 minutes. So we are all fair and square. We are quits. We're equal. Yes. who is right? So what you should do, guys, calculate. No one. I was expecting you to say me, because I'm always right. So calculate. First of all, confirm, is it true or not? What's the expected value? On average, what's the expected value that Dave waits for me? All right, let's calculate it together, I guess. So it's true that A is 5. You remember the expected value of a uniform is always the midpoint. So it's from 0 plus 10 divided by 2 is 5. Yes? So expected value is 5. You all agree with me, yes? You remember how to calculate expected value of uniform random variables. Next is what's the expected value of Dave, right? How long does it take for Dave to exit? The expected value for him to arrive regardless of the situation, if it's scheduled at 12, is it's just this expression t multiplied by the density function, and you integrate it, and you recognize it, of course, as, well, it's a integration by parts process. So you do the integration by parts. Here it is. Yes. And what do you get? This disappears to 0. And you just get the integral from 0 to infinity of e to the minus t over 10 dt. And this part is just equal to 10. You, by the way, if you can remember it, if you have an exponential random variable with parameter lambda, you see lambda is in this case 1 over 10. Yes, the expected value is 1 over lambda. We did it already, just 1 over this number. So it's when this expression, when you see the product of t to this is equal to 1. So t is going to give you then the expected value. So t is 10 for that. Good. So the expected value is 10. So that means that when he visits me, he waits on average 5 minutes. It is true. And when I visit him, my average waiting time is the expected value of d minus a. Right? It's the time, d is when he exits, a is when I arrive. So d minus a is how much I wait for him. Do you agree? And that expected value is expected value of d minus expected value of a, which is 10 minus 5, it's 5. So that means on average, I wait for him, because I implement the Dave correction time, I wait for him exactly the same amount as he waits for me. Good? So on average, we wait for each other the same amount, but the problem is, look at it. what's the probability that that I have to wait for him longer than 10 minutes? The probability I have to wait for him longer than 10 minutes, it's a double integral. Isn't it nice? Why is it a double integral? Well, look at it. It's the integral. Look at this expression, right? What is this? It's the same as the probability that d is bigger than a plus 10, right? It means that he exits later than my arrival plus 10 minutes. And I just took just out of the blue, just how likely am I to wait for him more than 10 minutes? Yes. So this is what? This is the integral from 0 to 10, probability that d is bigger than a plus 10 times the, you see what I do? It's just the probability that d is bigger than a particular a plus 10 times the probability of getting that a, which is approximately 1 over 10 a, the 1 over 10 dA, I'm sorry. Right, it's all for all of them, it's approximately 1 over 10, and dA is the short width of that rectangle. So you understand the way I do it is I always imagine actually solving a discrete problem. I don't like continuous problems, they're confusing. Discrete problems are well approximating the continuous case if you have a very large subdivision. And I can just very quickly move from imagining a discrete representation to the integral representation. You see it? So you all understand how I got this part, right? So it's this probability. Why do I sum it up? Because the actual probability of my arrival could be maybe I arrive at 0 at any given moment a. So this is conditional. Do you see? This is basically probability d bigger than a plus 10, given that capital A is equal to little a. Everybody understands? Yes, guys, it's very important, right? Because things like that are on the exam. If something is missing, please let me know. You understand how this is working. It's just a Bayes formula, and I just condition based on different values of a, and I add it all up. Just the addition here is enormously large. It has, let's say, maybe from 0 to 10, I divide it into a million different possibilities. And then if I divide it into those million different possibilities, each possibility is equally likely. This is the probability of it. And I add it all. Should I say more, guys? Should I write it slower, or do you understand? Write something in the notes, in the message box. Write yes, you understand, or if you have questions, I would like to correct it. Kate, do you understand it? Gustavo, Jacob, Albert, who understands it? Well, it will be double integral in a moment. You will see it. But right now, you see this part. I'm just trying to break this expression, right? So here I have probability that d is bigger than a plus 10. So how can I calculate this probability? I would like to condition it on what a is equal to. So a could be 0 or some other value, right? So just for any given a, the probability that d is bigger than a plus 10 is this. So it's this probability multiplied by the probability that a is actually this value. Okay, so this is d bigger than a concrete a plus 10, given that I arrive at moment a, and approximately my arrival at moment a is here. I hope it's understandable, right? And then how do I calculate this? Now what is d? So here I have, I want to expand it. So here is so what is the probability that d is bigger than a plus 10? It means that, it means what? It means that it's just the integral from a plus 10 to infinity of 1 over 10 e to the minus t over 10 dt. Right, this is the probability for any fixed a. The probability based, because it's exponential distribution, right? It's exponential distribution. The probability is just add up over all values of d that are bigger than a plus 10, right? And the values of d are like skyscrapers. They're essentially, what are they? they are 1 over 10 e to the minus t over 10 dt. So those are the values of d that it can take. So that's for t equal to a plus 10. And then for any other t, I just add them up. This is just not conditional. This is just adding up over the many thin skyscrapers of the exponential variable, right? So you see, that's why I wrote it like this. So just this probability is the integral involving only t, right? So we have now a double integral. Do you see where the double integral comes from? You have, on one hand, a varies from 0 to 10, and t varies from a plus 10 to infinity. Yes? So we have this expression, and then we integrate. So how do we integrate? So we first integrate from a plus 10 to infinity. We get this number. Just an integral. So the inner integral, when you carry it out, it's possible. Just e to the minus t over 10, and evaluate it from those two values, and this is what you get. The 1 over 10 is from here, and then here you integrate from 0 to 10, and this is what you get. And this results in e to the minus 1 minus e to the minus 2, which is 0.23, which means it's 23% likely that I have to wait for him more than 10 minutes. And that me being very generous. It happened very often. I would wait for him for 40 minutes or 1 hour. Yes. You see? So although on average we wait for each other the same amount of time, there is no chance he will wait for me for more than 10 minutes. Whereas the chance that I will wait for him longer than 10 minutes is 23%. Yes, the value, then the average is not the same as the distribution. Yes. Wonderful. And now we move to the last few topics. So let's talk about jointly distributed random variables. So here we first want to talk about the joint distribution functions. So the cumulative distribution of two random variables x and y is defined to be capital F of AB. And that's the probability that x is less than or equal to a and y is less than or equal to b for a and b between minus infinity and infinity. Yes. And from this information, we can derive the, it's called marginal cumulative distribution, I think, of just x. And that's just x by itself. Let's say if I have two variables, I want to know the behavior of only one variable by itself, I can do this. I can create the cumulative distribution for x, and that's just the probability that x is bigger than a, and that means y can do anything it likes. It's less than infinity means it can do anything it likes, and x is less than or equal to a. And what is this? This is the probability of the limit as b goes to infinity, x less than or equal to a, y is less than or equal to b. And we know that we can push the limit outside. This event is growing, it's becoming larger and larger event. And we know that for a sequence of increasing events, the limit of the probability of the limit is the limit of the probability that we covered in chapter 2. So it's this expression, you see, which you can just as well think of as capital F at a infinity. Good. So just plug instead of b infinity, and that's what you get. Good. And similarly, the cumulative distribution of y, just plug infinity instead of the x. As I mentioned, so when you deal with continuous random variables, the cumulative distribution is very useful too. And in general, any probability question, at least in theory, can be answered if you know the cumulative distribution. So for instance, suppose that I want to calculate the probability that x is bigger than a and the probability that y is bigger than b. How do I answer it in terms of the cumulative distribution? Well, I can begin by looking at this number and saying, okay, well, that's the same as y bigger than b and x less than infinity minus x less than or equal to a, y bigger than b. Do you agree? If I remove one from the other, then I get this expression here. Yes, because really what happens here? Those two events are disjoint. You cannot be sorry, not disjoint. So what happens here is I am just you can imagine taking intersections. This means X can do whatever it wants, and here I remove the possibility that X is smaller than A. So that's what we have here. And then I underlined it in red because I'm going to look at this probability and I'm going to break it further. I'm going to break it now by the Y. So here Y is bigger than B. I make it Y can do anything it wants. It means Y is less than infinity minus Y is less than or equal to B. You see that? So this now is equal to this minus that. And what I underlined in blue, it's equal, you see, because of the minus, it's which is sign, but this in blue is just this probability minus this probability. And because there is a minus sign, I have that this equals to this plus that. Make sense? It's just the intersection of sets. I mean, we did the same thing, just they're labeled differently here. Make sure that you understand, guys, and make sure that it's easy for you. So what do we get? We get 1 minus this first part is the first part here is 1. What is this part? This means we have we have infinity instead of A, and we have B, and here we have for this part infinity instead of Y, plus the capital F function at AB. This is now the calculation, you see, and that means that we can just figure out the entire expression in terms of the cumulative distribution. Here is another example. Suppose I have X between A1 and A2 and Y between B1 and B2. And I want to express this probability in terms of the cumulative joint distribution for X and Y. So what do? I again break it apart, you see. So what I do here is I first break the X apart and don't bother the Y. You see the Y is staying the same. Break the X apart. So it's the probability that X is less than or equal to A2 minus the probability that X is less than A1. And you see I don't bother the Y. And then once I finish breaking the X apart, I continue breaking the Y apart. So you see what's in red is breaking the Y apart. And what's in blue, I break here this Y apart. And this is what I get. Yes, which reduces to the expression you see here. More or less good, yes? The point of those examples, you do that also in measure theory, is just that you can see that you can solve any problem about probability. If you are given the cumulative distribution, you can figure out how to rewrite any other problem in terms of the cumulative distribution and therefore solve it if you know this function. So if X and Y are discrete random variables, we can define the probability mass function at X and Y to be the probability that capital X is little x and capital Y little y, and the probability that of just X, probability that capital X is equal to X, is just the summation of those probabilities for all possible Y's. And similarly, the probability for each fixed for a Y variable to equal to Y is the summation over all Pxy, where X varies over the entire real number line. That makes sense, yes? Because if I just say what's the probability that the first coordinate is equal to 1, that means the second coordinate is allowed to do whatever it likes. And I add over all probabilities where the first coordinate is fixed at 1 and the second coordinate is doing whatever it likes. Right? So here is just a few examples. 3 balls sampled randomly from urn containing 3 red, 4 white, and 5 blue balls. If X is the number of red balls in sample and Y is the number of white, the joint probability mass function is given by, here, you see what happened here. So we have 3 balls from an urn containing 3 red, 4 white, and 5 blue balls. Okay, so X is the number of red and Y is the number of white. Right? So how many could we have? So we could have had 0 and 0. So 0 red and 0 white. And that means that we chose all 3 from the 5 blue. So it's 5 choose 3 divided by 12 choose 3, because we can select out of 12 balls in total any 3. And this is the probability, yes? So this is the first column here. Begin here is where x is 0 and y something else. And you can see you can carry out lots of those calculations. Make sense? So you can see here it means that I have, I think, 1 red and 1 white, which means I had to select 1 blue because my sample contains 3. So you have all those many probabilities, and it's nice to put those probabilities in a table. Okay. So you see, you can write a table, and here is I, that's how many you have of one category, and J, how many you have of the other category, because our sample is of size 3. Make sense? This way it's easier to track the information. So for instance, what's the probability if the first was what? The first was white. The first one, sorry, is red, and the second one is white. So for instance, this might be how many red we have, and this is how many white we have, you see? And of course, some possibilities cannot happen. Some of them are 0 because, for instance, I cannot have 3 red and non-zero white. Agree? Because the sample is, I have exactly 3 balls altogether. Make sense? And then what is this column? For instance, you see, I can sum it all up. So this number plus this number plus this number plus this number, I can sum it up here. What is this number representing? That represents the probability that I have 0 white balls. Right? If I have 0 white balls, I might have 0 red balls, or 1 red ball, or 2 red balls, or 3 red balls. Make sense? So the rows here represent, if you add up over the rows, you get this coordinate fixed, the x coordinate is fixed. Over the columns, that means the y coordinate is fixed. Makes sense, right? And the reason it might be called marginal probabilities is because it's as if this is on the margins, you see? The summation is probably here, it's on the margin. So that's what is this number? It's y equals 0, right? What is this number here? It's x equal to 3. This number here is x equal to 3. Yes? So it's marginal, maybe because it's written on the margins in the table. Maybe that's why they call it this way. That's my guess. Okay. So now we talk about a little about jointly continuous variables. So x and y are jointly continuous if there is a continuous function f(x,y) such that the probability that xy is in C is the double integral of f(x,xy) dx dy. Okay, why would you have a double integral? It's a similar thing. It's the same analog with cutting the hair, but now imagine what you do is you throw a ball on a rectangular grid, right? And maybe with very fine mesh. So you just measure in which rectangles the ball first hits the floor. So you randomly throw the ball, and maybe it hits on the floor in one rectangle or another rectangle. Actually, next class, maybe I forgot to bring it today. I forgot I have this very nice toy to help you understand this distribution, right? I will bring it next class, as we just only have 5 minutes if I can easily find it. Okay, so I would like to explain in that distribution why do you have this double integral if you don't see it. All right, so just for now, let's just move on. Capital FAB is then the probability that x is less than a and y less than b, and that's this integral, double integral. Clearly, because if x is less than a, it means we integrate from -infinity to a, and if y is less than b, we integrate on the y-axis from -infinity to b. And we can find the density function by taking 2 derivatives. So take the first derivative with respect to, just look at it. Just this is derivative with respect to A and derivative with respect to B. It's this expression. So if you take the derivative with respect to B, it's the derivative of this expression. Look at it. Take the derivative of the outer integral with respect to B. B replaces y and the integral disappears. And I'll take derivative with respect to A drops down into x, and we have FAB. It's just applying the fundamental theorem of calculus. You just apply it twice. You see, each time you apply it, you will get rid of one of the integral. So if I take the derivative of this expression with respect to B, I get rid of the integral having B on the top and dy. And that's what you see over here. You see, first I apply the B. It gets us to this expression. Then I apply the derivative with respect to A, and it gives us this expression. Clear? Yes, well, we'll make it clearer very soon. So the probability that x belongs to A, what is that? That just means that y can do anything at once. It's the integral over A of y doing anything at once. And what is that? This expression is just the, if you think about it, it's just the marginal distribution for x. Yes? You can see we add up all the probabilities that where x is fixed and y is the probability that x is a particular value and y is just moving around. It's just like this formula over here. You see, same thing. They are exactly identical. Well, I see that they're exactly identical, but do you? All right, let me write it. Here, guys. So suppose I want so we have the probability that x belongs to A, right? What is this? This is integral A, integral minus infinity, infinity, fxy dy dx. So this statement, do you understand? Makes sense, right? Because if I don't mention y, it means y can do anything at once. Yes. And then what is this expression? What is this expression? Yes, we can understand it. It's not hard to understand it if you just think, what is it generating? So if I want, let's say I want the probability of x equal to little x. Yes, not just in any a, just x equal to little x. What am I going to do? I'm going to say, okay, well, this is the summation for any y belong to R. Y can do anything at once. Probability x y, right? And what's probability xy? If we have this function, the probability is simply here y belongs to R. The function is what? The function is little f x y dy. So if you multiply this by dy, it's kind of like the probability that we have for a given fixed y. This is what we get. Right, we just gather all the probabilities where this is the density where y is fixed. So we get this is then the probability that x is equal to x. You might actually want to multiply it if you say this is really similar to x being between x and x plus dx. Then maybe you can say, if you want to, you can multiply it by dx, but there is nothing integrating here dx. So it's just basically the integral from minus infinity to infinity fxy dy dx, right? The dx is just, so don't worry if it's just the lesson is almost over. If the last few things I said are confusing, I will try. I forgot to bring that toy. I actually bought this nice toy for you to hopefully illustrate the density function easy, right? I have a very nice illustration using that toy. Hopefully you'd like it. And you will see it next class. So guys, any questions, any wishes? I'm gonna stop the recording.